Welcome to my virtual HotEdge 2020 talk on synthesizing plausible infrastructure configurations for evaluating edge computing systems. My name is Thomas Rausch from the Technical University of Vienna, and I first want to motivate this paper by explaining why we started working on synthetic infrastructure configurations in the first place. At last year's HotEdge, we presented the conceptualization of a platform for deploying AI applications as serverless functions to edge infrastructure. And the claim was that we could improve existing serverless container schedulers to make better function placement decisions when they use edge resources, particularly when those resources are geographically distributed and extremely heterogeneous, which are two characteristics that we typically ascribe to edge systems. So we built a testbed using different compute platforms and typical edge devices and deployed our platform prototype. But when it came to designing an evaluation to validate the claim, we figured that we had to show that our platform would make good placement decisions in many different infrastructure scenarios, and the testbed was just too simple to allow any kind of credible generalization. So when we started looking into other application scenarios and what the infrastructure and the network topology in these scenarios look like, we encountered some research gap, which is part of what this paper is about. First, we looked into different edge system simulators, which typically provide some way of describing an underlying infrastructure. The problem with these approaches is that either the configurations that come out of them turn out to be very use case specific because someone needs to manually design them, or that they're not representative of edge systems because they're generated randomly or represent internet scale topologies. But what is representative of edge systems? What does edge infrastructure look like? Unlike in cloud computing, where the infrastructure is just racks and server computers, there's no real consensus in our community on what exactly edge infrastructure looks like. Satya and others have tried to come up with a framework for thinking about edge computing landscape, but still the concrete infrastructure and network topology really depend on the particular use case and scenario. So we thought it would be useful to look into different scenarios where a type of distributed compute fabric emerges that is composed of different edge devices and that would be suitable for something like a serverless edge platform that we were proposing. In the paper, we have a description for each of these scenarios. We have some data on existing systems that fall into these categories. And we also have concrete numbers on the type of edge devices, the network parameters of particular deployments, and so on. So if you're interested in that, I encourage you to find the details in the paper. A specific existing system in the category of urban sensing is the Array of Things project that has a deployment of about 200 of these sensor node boxes in Chicago. Basically, these arrays contain sensors and two single-board computers that can run some computation. They're connected mostly via mobile internet, and we expand on this idea in the paper by coming up with some plausible extensions to the existing deployment by, for example, considering proximate edge compute resources for running, say, AI functions. And now we wanted to generate plausible infrastructure configurations and network topologies for these different scenarios based on the numbers we had defined and use them as input for a simulator that we had built for our platform. So we extracted this as a Python tool called the Edge Topology Synthesizer, and I'll now present some of the key ideas and the basic functionality. The conceptual model of the tool is very simple, but provides a very flexible way of creating edge network topologies. The first concept is just a node, so any type of compute device. We provide a bunch of different node types out of the box, like a single-board computer or a server computer, and they come pre-parameterized with same default values that you can override. So you could instantiate, for example, a Raspberry Pi 3 or an Intel NUC or something. Links are components that facilitate network communication, which have an associated bandwidth, and are used to form edge networks, or cells as we call them. The simplest cell in our model is just a network host, which is a node connected to a link, for example, a network card. And now these cells can be composed to form more complex topologies. This example shows an industrial IoT scenario where a factory floor is equipped with 3 single-board computers connected through a shared Wi-Fi link. The factory floor also hosts an IoT compute cell, in this case some embedded AI hardware and an Intel NUC, and an on-premises cloudlet. The tool gives you these cells as building blocks, so you can, for example, instantiate the cloudlet by simply passing the number of racks and server computers, and the tool will create the cells create the necessary components for you and connect them to form this LAN cell. Cells can be composed hierarchically and then connected to the internet through separate up and down links. So our tool also provides common uplink configurations, for example, up-downlink speeds associated with a business ISP or a fiber optic network. So you can see that the model really focuses on the high-level topology of edge systems rather than, for example, the internals of the internet backbone. We want to be able to parameterize these cells, and it's an important part of synthesizing cells. And we also think it's an interesting aspect that we should explore more in general, namely finding out which parameters actually underpin edge systems and topologies. So an abstract property like a degree distribution probably won't be very useful. But as I've mentioned, most cells can be parameterized with size parameter. What we haven't fully implemented yet is a type of cell entropy that puts a number on the heterogeneity of a cell. So for example, the heterogeneity of a server rack with the same type of server computer would be 0. Whereas if you want to synthesize a cell with many different compute devices or varying compute and storage capacity, you would pass a high value for heterogeneity. We think this is maybe a useful parameter to adjust when you're doing evaluations to answer questions like how well your particular system can deal with heterogeneous infrastructure. Density is another useful parameter that I want to motivate with an example. In the course of exploring different infrastructure scenarios, we were looking at the distribution of particular nodes in a geospatial context. So for example, on the left-hand side, you can see the city of Chicago and the distribution of these array of things nodes in the neighborhoods of Chicago. The figure on the right shows the distribution of mobile base stations in my hometown of Vienna. We fitted log normal distributions over both of the density histograms and saw that they fit very well. And we found it useful to be able to pass these distributions as parameters when synthesizing cells. So when you're creating a topology, for example, that spans a city, you can create a template for a cell, and then the number of nodes in that cell will vary according to the distribution that you define. Here's a complete code example. This piece of code creates an urban sensing scenario topology that we talked about earlier. So you can define nodes and then use them as a template. So for example, one of these urban sensing nodes is an IoT compute box with 2 Raspberry Pis. A neighborhood has a size which defines the number of sensing nodes in that neighborhood. The neighborhood is connected via a 500 megabyte per second shared link, for example, a long-range Wi-Fi, and connected to the internet via a mobile internet connection. We then put the neighborhoods in a geospatial context, which we pass a density distribution as a parameter, so that the number of nodes in a neighborhood will vary according to this density function. The city also has a municipal cloudlet, which has like 10 servers in 2 server racks connected via fiber connection to the internet. So these are the primitives that our tool gives you, and you could now wrap this code as a reusable scenario and create some high-level parameters. In fact, we already have 3 such scenarios that you can just instantiate, and we're happy to receive contributions or suggestions on other scenarios. The code creates a graph structure using the Python library NetworkX, which can then export the topology into various different graph formats. Our tool also provides static latency graphs of various internet backbone topologies that are derived from online datasets. and allow you to interconnect your local topologies, which gives your topology some coarse-grained latency information out of the box. And these generated topologies can be used in various ways. So for example, here you can see an IIoT topology that we generated with our tool in a visualization that shows the bandwidth utilization data from a network simulation that we've built. And you can see the individual cells of the IIoT example that we showed earlier. So to conclude, we hope that this framework can create value for the community. We've started using it internally to generate input for evaluations that use network simulations. And maybe this work can foster a discussion about evaluation methodologies for edge systems in general, and also what type of infrastructure we should consider when building such systems. So thank you for listening, and please engage with us via email or on GitHub.